A powerful storm can dump the equivalent of dozens of Olympic-sized pools onto a single city in less than an hour. Now imagine that happening all at once across thousands of streets, rooftops, parking lots, and avenues. If all that water simply stayed where it fell, no city would survive. Cars would be swept away, stores would be submerged, homes would turn into islands. But that doesn't happen right away. Before the flooding appears, before water invades homes, something begins working in silence, and almost no one notices. So the real question is, where does rainwater go before flooding begins? Because it doesn't disappear, it doesn't evaporate, it doesn't vanish by magic. It enters a massive underground system, hidden beneath asphalt, beneath sidewalks, and even beneath entire buildings. There is a true parallel city beneath your city. Tunnels wide enough for a truck to drive through. Reservoirs capable of storing millions of liters at once. Metal gates that open and close automatically to control the flow. And all of it begins working the exact moment the first drop hits the ground. Welcome to Invisible Structures. Today, you're going to discover how these colossal systems work. Systems almost no one sees, yet they keep modern cities running. You'll follow the path of water from the moment it hits a rooftop to the point it's released back into rivers and channels. And here's the most impressive part. Some of these structures are so large, an entire building could fit inside them. But here's what most people don't realize. These systems have limits. They're designed based on volume, time, and rainfall intensity. When that limit is exceeded, the city loses the battle. And that's exactly when flooding begins. Stay until the end, because you'll start seeing your city's streets in a completely different way. And if you like uncovering the hidden systems that keep the world running without anyone noticing, subscribe to Invisible Structures now. Because after this video, a simple storm drain on the sidewalk will feel like the entrance to something far bigger than you ever imagined. It all begins in the most ordinary place possible, your roof. When rain falls, the first surfaces it hits are rooftops, balconies, awnings, and terraces. Within seconds, water starts running through gutters and down side pipes. Now multiply that by millions of buildings at once. Every structure dumping water almost simultaneously. Every home adding a few more liters per minute. And it's not just rooftops. Asphalt streets, parking lots, industrial yards, malls, airports, concrete sidewalks. All of these prevent water from soaking into the ground. It simply runs off. And the more urbanized the city, the faster it moves. In natural areas, part of the rain seeps into the soil. In cities, it accelerates. It's like comparing a sponge to tile flooring. The sponge absorbs. The tile sends water racing. And once it moves, it needs an immediate destination. That's where storm drains come in. Those grates along the sides of streets may look simple, but they're placed strategically at the lowest points in the urban landscape. Engineers study street slopes, elevation changes, and water flow to decide exactly where each one goes. Beneath the grate is a catch basin. It doesn't just hold water briefly. It also acts as an initial filter, trapping leaves, plastic bags, and larger debris. Without this step, the entire system could clog within the first few meters. And here's an important detail. Many floods begin precisely when these inlets are blocked. Sometimes it's not a lack of infrastructure, it's poor maintenance or improper waste disposal. When the catch basin fills up, water can't flow downward as quickly. It starts to build up, but assuming everything is clean and working, the water enters the underground pipes. These pipes vary widely in size. In residential areas, they may be just a few inches across. In central districts, they can exceed a meter in diameter, and they're not placed randomly. Every segment is calculated. Engineers analyze rainfall history, drainage area size, and how long water takes to reach the lowest point. Everything is designed to prevent overload. Smaller pipes feed into medium ones. The medium ones feed into main lines. It's like an inverted tree. Small branches join into larger limbs until they reach the trunk. During heavy rain, thousands of liters per minute move through this network. And all of it happens beneath the asphalt you walk on every day. There's also another key distinction. In modern cities, stormwater systems are separate from sanitary sewer systems. This is critical. Because if rainwater mixes with sewage, the volume increases drastically and can overload treatment plants. When that separation doesn't exist, the risk of backflow rises, and the problem goes beyond flooding. But even in well-designed systems, there's a physical limit. Imagine draining a tank through a fixed pipe. If more water enters than can exit, the level rises. It's pure math. And the more impermeable the city becomes, the greater the volume arriving at once. And if you're impressed, realizing every street hides a network engineered with this level of precision, hit like now. It helps invisible structures keep revealing what holds cities together behind the scenes. After passing through secondary pipes, the water reaches the main channels. By now, the volume is significant. In some areas, the flow can exceed thousands of liters per second. And speed matters. If water moves too fast, it can cause internal erosion. If it moves too slowly, it can lead to buildup. That's why diameter, slope, and internal lining are carefully designed. But even when everything works perfectly, rain doesn't wait. If intensity suddenly spikes, the system begins operating near its limit. And that's exactly where the larger structures you'll see next come in. Because when simply moving water isn't enough, it has to be stored. And what engineers have built to do that is far bigger than most people imagine. So far, you've seen how water enters storm drains and moves through a precisely engineered underground network. But there comes a point when simply moving it isn't enough. As rainfall intensifies, volume rises too quickly. Main pipes begin operating near their limits. That's when the city activates its second line of defense: large galleries and retention reservoirs. A few meters below the street, you'd find concrete corridors wide enough to walk through, sometimes slightly hunched, sometimes fully upright. These main galleries receive water from multiple neighborhoods at once. We're not talking about small flows. During heavy storms, a single channel can carry thousands of liters per second. To picture it, imagine dumping a full water tank every few seconds into an underground corridor, and the water keeps coming. These galleries are built with precise slopes to maintain ideal speed. If water moves too fast, it erodes the structure. If it moves too slowly, sediment builds up. Everything has to stay balanced. But when calculations show that transport alone won't be enough, massive reservoirs come into play. Many people know them as stormwater basins. What most don't realize is their true scale. Some occupy the space of an entire city block. Others are hidden beneath parks or wide avenues. They're like artificial caverns built to temporarily store millions of liters of water during peak storms. In theory, the system is simple, yet in practice, it's impressive. When sensors detect a rapid rise in flow, internal gates open. Part of the water is diverted into the reservoir, where it remains until river levels drop or the main system regains capacity. It's as if the city has emergency tanks ready to absorb the excess. And these tanks aren't small. Some can hold the equivalent of tens of thousands of tanker trucks. All of it hidden underground. And here's something striking. Many of these structures sit directly beneath everyday public spaces. Parks with children playing, packed parking lots, even soccer fields. Beneath them, there may be vast empty space waiting for the next storm. But there's another essential element: monitoring. Today, many of these systems are equipped with level sensors installed at strategic points. These sensors send real-time data to control centers. If levels rise too quickly, operators can redirect flow to another reservoir or adjust the sequence of gate openings. It's almost like a traffic control center, but for water. And everything has to happen within minutes. Because a severe storm doesn't give days of warning. Its intensity can shift in moments. Now, let me ask you, in your city, have you ever seen a major drainage project being built? Have you noticed a park or plaza renovated with the promise of reducing flooding? Drop a comment with the city you're watching from. It's fascinating to see how each region invests, or doesn't, in these invisible systems. There's a huge difference between cities that have expanded their reservoirs over time and those still relying on projects designed decades ago. And here's something many overlook. As cities grow, they gain more concrete. The more concrete, the less water infiltrates the ground. Less infiltration means more water hitting the system all at once. It's a shifting equation. If infrastructure doesn't grow with it, the risk increases. That's why some cities have begun investing in even more extreme solutions. Not just galleries, not just reservoirs, but massive tunnels with diameters comparable to subway stations. In the next segment, you'll see how these mega-tunnels work and why they cost billions to build. Because when rainfall exceeds every calculation, only truly colossal structures can buy time for a city to keep functioning. When the galleries are already at their limit, when the reservoirs are nearly full, that's when what many engineers call the final line of defense comes into play. The massive underground tunnels. These structures weren't built out of excess caution. They were built because without them, some cities simply couldn't survive modern storms. We're talking about tunnels 10, 12, even 15 meters in diameter. To grasp that scale, imagine a 5-story building laid on its side underground. Now picture kilometers of that building running beneath an entire city. These tunnels sit dozens of meters below the surface. So deep they pass beneath building foundations, subway lines, and infrastructure networks. To build them, massive machines called tunnel borers are used. They don't just dig. They grind through soil, install reinforced concrete rings, seal the structure, and move forward slowly, meter by meter. Each segment weighs tons. Every mistake can risk billions in investment. Progress is almost surgical, sometimes just a few meters per day. It can take 5, 8, even 10 years to complete a single system. But when the storm hits, all that effort has to work flawlessly. During extreme rainfall, massive metal gates are activated. Part of the flow from the galleries is redirected into these deep tunnels. Water rushes downward with force. Millions of liters per minute can surge through these corridors. It's no exaggeration to say some of these tunnels act like artificial underground rivers. And the sound inside, at peak flow, is deafening. It's like standing inside an invisible hydroelectric plant. Meanwhile, on the surface, people only see the rain falling. But below, sensors monitor everything: internal pressure, flow speed, water levels. Control centers receive real-time data. If a section nears capacity, engineers assess how to redistribute the flow. But there's an unavoidable truth. Even these colossal systems have a maximum limit. If rainfall intensity exceeds the tunnel's capacity, the system begins to fill completely. And once it reaches its absolute limit, there's no space left to absorb the excess. That's when every minute gained matters. Because these tunnels don't eliminate floods, they delay them. They buy time. Enough time for the storm's peak to pass. Enough time for receiving rivers to drop. Enough time to keep water from invading thousands of homes. Without these tunnels, the impact would be immediate. Streets turning into rivers within minutes. Basements flooded. Subway systems shut down. Billions in damage within hours. That's why some of these projects cost billions. Because prevention is expensive. But collapse can cost far more. Some cities have built tunnels so extensive they could span entire districts. Some systems stretch for dozens of kilometers. Its infrastructure comparable to a subway line, dedicated entirely to stormwater. And the most striking part is the contrast. Above ground, horns, lit buildings, people walking. Below, a massive current rushing through concrete corridors as tall as a building. All to keep the city running. And when it works perfectly, no one notices. But when it fails, the city feels it immediately. Enjoying this? Now you'll see why, even with all this monumental engineering, some floods still seem inevitable. Because there's one factor no tunnel can fully control. Even with deep galleries, massive reservoirs, and tunnels the size of buildings, there comes a point where the equation simply breaks. Imagine every system operating at once, storm drains capturing at full capacity. Because there's one factor no tunnel can fully control. Even with deep galleries, massive reservoirs, and building-sized tunnels, There's a point where the equation collapses. Imagine every system running at once, storm drains maxed out, pipes completely full, reservoirs nearly at the top, megatunnels carrying millions of liters per minute. Now imagine the rain intensifying even more, heavier, more concentrated, faster than any previous record. When incoming volume exceeds everything that can be stored or carried, the excess doesn't vanish, it comes back, and it returns exactly where it entered, through the streets. That's when flooding begins. Not because infrastructure doesn't exist, but because it's been overwhelmed. And this is happening more often around the world. Storms once considered rare are now repeating. Cities designed decades ago are facing volumes never included in original calculations. And there's another factor no tunnel can fully control: the pace of urban change. Every new building adds more impermeable surface. Every new parking lot reduces natural infiltration. Every expansion accelerates runoff. The modern city is efficient at functioning, but unforgiving when it comes to absorbing water. As natural ground disappears, underground systems must compensate. And eventually, expansion means digging deeper, investing more, and planning for increasingly extreme scenarios. But here's something few people realize. Even during severe flooding, most of the system is still operating. It hasn't stopped. It hasn't completely failed. It's simply been exceeded. And that changes how we see the problem. Because it's not just about a lack of infrastructure. Often, it's about physical limits in the face of increasingly intense events. There's another detail that often goes unnoticed. After the rain ends, technical teams enter these galleries and tunnels for inspection. They check for cracks, remove accumulated sediment, inspect gates, and test sensors. Because keeping this underground city running requires constant vigilance. Without maintenance, risk grows silently. And here's one last image to keep in mind. The next time you walk down a wide avenue or cross a busy square, imagine what lies beneath. Massive corridors, empty reservoirs waiting for the next storm, deep tunnels ready to receive millions of liters, an invisible city supporting the visible one. And now you know exactly where rainwater goes before flooding begins. It follows a calculated path, passes through monumental structures, and depends on engineering that works in silence. If this video opened your eyes to something always beneath your feet, subscribe to Invisible Structures. Because here, you discover what keeps the world running when no one is watching. And tell me in the comments, what changed your perspective the most today? The scale of the tunnels? The hidden reservoirs? Or the fact that all of this happens without us noticing? The more we understand these systems, the less a city is just concrete, and the more it reveals what truly sustains it.